Well, greetings, friends, and welcome back to my sequence of YouTube videos that I hope will be helpful to you as you're beginning your academic journey into the exciting world of electronics technology. We begin today's lesson with Ohm's law calculations for series circuits in DC electronics topic number 4 by the KOGUY. Most of the theory pertaining to my YouTube videos is pretty well covered in your assigned textbook for reference, but I will cover the theory as it is needed in the slides forthcoming. There will be emphasis on the hands-on work that we're about to do, both with the calculator as well as with our digital multimeters. So let's go ahead and go to the next slide. All right. So what is Ohm's law? Ohm's law states that the three basic electronic quantities have a unique relationship with each other. Now, I showed you this slide before that I borrowed from Pinterest, and it shows the relationship between resistance in units of ohms, which is the cowboy with the lasso, and then voltage, volt, which is the unit of voltage, being the pressure that moves the electricity along. And the electricity is shown by the little green character, amp. Amp is the unit that is designates the amount of current that flows through a channel, a conductor, a wire. And so you can see there's a direct relationship between the amount of resistance that will constrict this water hose to the amount of current that can be pushed through. So formula-wise, there's a unique relationship given by Ohm's law. And so we have, let me read this to you, voltage, the first bullet point, is equal to current times resistance. And you can see the formula written as V equals IR. Now, the little dot for multiplication is implied, and you won't necessarily see the dot or an X or an asterisk in here. By having the I and the R does infer that they are to be multiplied. So V is equal to I times R. Current is calculated as voltage divided by resistance. So V is equal to I is equal to V over R, whereas resistance is calculated as voltage divided by current. So R is equal to V divided by I. And taking this one step further, if you recall, the electrical units table that I'd given to you before in a previous discussion is available to you in the Patreon link in the notation of the YouTube in its complete form, but I've expanded it for this discussion to bring in power. Previously, we had voltage, we had current, we had resistance, and now I'm adding power. So just to review, the quantities of the electrical units table are shown in columns where I have symbol for the quantity as it is read, the units for those quantities, the symbol for the unit, a brief discussion, and which scientist gave us this particular set of quantities. And so V for voltage, I for current, R for resistance, P for power, but the units are very unique. The voltage units are called volts. The current units are called amperes or amps, symbol A. Resistance units are measured in units of ohms, shown by the omega symbol, and the units for power shown in watts for the capital W, given to us by James Watt, a Scottish engineer. The formulas are shown very often as either circles or triangles. And so you have a circle here, V, IR, and then you also see EIR, and in triangular form, V, and there's an IR, and there's an EIR. And so the relationships mathematically are very easy to discern. Actually, let me clarify. Why do you see E in here? What does E represent? If you look at the second bullet point, it says E, V or E both represent the concept of voltage. V for voltage, or E for what? EMF, which is electromotive force, which is another way of describing voltage. So in some textbooks, you may see these formulas with an EIR, and in some textbooks, you might see this as VIR. They are the same. The fourth bullet point, the horizontal line in these circles or these triangles represents the math function called division, and the vertical line represents multiplication. So we can derive three different variations of Ohm's law formulas from any one circle or any one triangle. So if we take a look at this triangle here, we have the V and we have the I and the R. And remember, the horizontal line represents division. The vertical line represents multiplication. If we are looking for a calculation of voltage, what you do is you take your thumb right now and you put it over the letter V to cover it up with your thumb. And what's left underneath your thumb is you should see I. There's a vertical line here which represents multiplication, I times R. If we're looking for, in the middle triangle, if you're looking for current, put a circle around that, put your thumb over that I. And if you're looking for current, you put your thumb over the letter I, and what's left in the triangle or circle is you have a V up on top, you have an R down below, and remember the horizontal line represents division. So formula-wise, we would write this as I is equal to V divided by R. Lastly, is the third variation, and that is if we cover up our the letter R, let's say that's what we're calculating is the value of resistance. If you know 2 out of 3 quantities, we can calculate the third. So by putting your thumb over R, what do you see left outside of your thumb is a V on top and an I down below. So the formula is R is equal to V divided by I. So from one simple circular illustration or triangular illustration with an explanation of the horizontal line and the vertical line, you can discern a mathematical formula as long as you know 2 out of the 3 quantities. So just as a reminder, tip for success, and that is do chronicle your learning lessons into your journal as you accumulate the information from our video slide set. And so I recommend you putting your information in a journal, which can be in any of a number of forms. I've discussed this in a previous topic video. And specifically what I have here is sample page 3, because we're talking about Ohm's law and we're talking about these electronic terms. And you can see how this has been transcribed from lecture notes or from my videos onto your journal, and by having them in your journal. By having them in your journal gives you a very quick access to the concepts of interest. Okay. All right. Now we're going to apply this a little further, and we're going to do just a little bit of math. You don't need a calculator for this. Hopefully you should be able to do this in your head. So first bullet point, if we look at the schematic, before we look at the bullet points, if you look at the schematic, we show a voltage source, a resistor, and we're going to calculate either voltage, resistance, or current, depending upon which quantities we are given. So first bullet point says, with Ohm's law, if you have 2 out of the 3 quantities, you can calculate the third value. Easy. So if R is given as 4 ohms and I is given as 3 amps, now this is where you need to go to that table of electronic units and understand that omega is the unit symbol for resistance, and capital A is the unit symbol for amps or amperes, which is the unit for current. So as I'm reading this, if R resistance is given to you as 4 ohms and I is given to you as 3 amps, then voltage is calculated as I times R, which you can see in this first triangle. V is equal to I times R, because we have the I at 3 amps, we have the R at 4 ohms. So when you multiply the 3 amps times the 4 ohms, you can do this in your head. What's 3 times 4? 12. But what units is this 12? Is this 12 ohms? Is it 12 amps? No, you're calculating for voltage. So the units for voltage is volts. And what is the symbol for volts? A capital V. So the answer for this first calculation is 12 with a capital V designating volts as being the answer. Now, next bullet point, if the voltage source above is equal to 10 volts and the resistor is equal to 2 ohms, what are we looking for? What's left over? You have the V, you have the R, you're looking for I. I is current. There's your second triangle. And if you look at the second triangle, you put your thumb over the letter I, what's left? V divided by R. So this is what we have. We have I is equal to V divided by R, which is 10 volts. Again, it's handy for you to write down the electronic symbol. So 10 volts divided by 2 ohms. So again, you don't need a calculator for this. What's 10 divided by 2? 5. But 5 what? 5 apples, 5 oranges? No, we're calculating current. So current, if you go back to our table, is measured in units of amperes. What's the symbol for amperes? Capital A. And this is where it's really handy for you to have that electrical units table written into your journal, so you can have your journal open up on the side and have the electrical units table handy. And as we're using these terms, so here's your electrical units table that I've transcribed into a quad rule notebook. And so by having this handy on the side, open to show these terms and abbreviations and symbols, then as we go through our calculations, you'll be able to keep better track of what symbols for these units. Let's do the last one. If the voltage source is given as 15 volts and the current, I is current, is given as 3 amps, so you have a V, you have an I, what's left to be calculated? An R, resistance. So look at the last triangle. If you're calculating for a resistance, you put your thumb, literally put your thumb over the letter R. What do you see left over in the triangle? V divided by I. So in this particular case, R is equal to V divided by I, in this case, 15 volts divided by 3 amps. So again, this is simple enough. You can do in your head. What's 15 divided by 3 is 5. But again, 5 what? 5 apples, 5 oranges, 5 lemons, 5 watermelons. You're calculating resistance, and it's important for you to, you don't have to memorize this, but if you use it enough, you will come to memorize it. If you look at resistance, resistance is the symbol R measured in units of ohms, shown by the symbol omega, okay? And if we go back one more, a couple more right here, resistance in units of ohms, resistance symbol is R, ohms symbol is omega. And so you got to keep these terms straight. What is what? And if you transcribe this into your journal, you'll have it open at your side, ready to help you along. Like I say, if you use it enough, you'll remember all of this. Okay, this is how we apply Ohm's law. Now, a little bit more. There's something called Watt's law. James Watt. Watt introduced us to the concept of power, and there are power formula circles. P equals I times V. Power is equal to I squared times R. V squared equal PR. We're not going to do power calculations for this particular training video, but I want to give this to you here so that you have some reference when we get back to this. And if we look at using the first circle, and taking a look at how do we calculate power? Well, if current is given as 2 amps and voltage is given as 4 volts, power, according to this first circle, is equal to I times V. So that works out to be 2 amps times 4 volts. And again, you can do the math in your head. What is 2 times 4 is 8. But now, 8 what? Watermelons, oranges, apples. Well, if you're calculating for power, the unit for power is watt. And what is the symbol for watt? A capital W. And you've seen this before, anytime you've ever changed a light bulb. 25-watt light bulb, 60-watt light bulb, etc. You see a W after the number. All right. This is just for your reference. So this was constructed, borrowed by our friends in Pinterest. And you have a combined set of formulas that is each of one of these 4 circles combined into one. Again, I won't take time to talk about this now, but it is a reference for you so that if you're looking for any one quantity, you can calculate it as long as you know two other quantities. So all of the power, P here in the middle, P in blue, can be calculated using this wedge formula, or this wedge. If you're looking for current, current can be calculated using the green wedge here, this green wedge here, this one here. If you're calculating for ohms, I'm only showing you V divided by I, but ohms can also be calculated using this V squared over P or P over I squared. If you're calculating for voltage, the only one I'm showing you for right now is I times R or R times I, but there's two other ways of calculating that as well. So this goes to show all of them combined into one very nice graphic. And again, you don't have to memorize this, but I do highly recommend that you transcribe this into your journal and you can make reference to it anytime you need. And the formulas are completely derived here. There happens to be total of 12 formulas from the combined circles. All right, Ohm's law, Watt's law applied. Now, let's talk about this. If voltage is given as 15 volts, R is equal to 5 ohms, then current is, we've done this before, V over R, 15 volts over 5 ohms calculates the 3 amps. Done. Given the above, if power is equal to, let's see, power equals P, which can be calculated as I times V. So from the first line, we calculated I as 3 amps. We are given voltage is 15 volts. So if we want to calculate the power in this case, power is equal to I times V, which is from this circle here. You put your thumb over the P, you see it's I times V. So what's 3 amps times 15 volts? 45 watts. Or another way of doing this is by using the second circle. You put your thumb over the P. What do you see left over? I squared times R. I squared. So I squared times R is equal to 3 squared, because 3 amps was what we calculated for current, I. So 3 squared times the R of 5 ohms. 3 squared is 9. What is 9 times 5? 45 watts. So we can calculate the 45 watts using formulas from this second circle. We can calculate 45 watts using formula from the third circle. We can also calculate it, won't take time to do that, but you can play with that. Calculate 45 watts given the parameters we have stated so far, and using the fourth circle. All of the above formula circles work beautifully. And these are a summation of Watt's law and Ohm's law and how they interact with each other. Now, there's practice, and you can practice here, and I've got this worked out so that you've got some math to play with, but if you follow these along, you'll be able to end up with the same results. And again, this is pretty easy math. You can do this with a basic supermarket calculator. Don't even need a fancy scientific one, but we'll talk about scientific calculators in a moment. Now, let's talk about this. Engineering notation, AKA. What's AKA? Also known as. So engineering notation is also known as metric notation. And why is this important to us? Engineering notation is the standard of the world to efficiently express either very large numbers or very small quantities. So that's to distinguish engineering notation from what we learned back in grade school, decimals, and what we may have learned in middle school, scientific notation. So let's go back to Ohm's law. You are given V, 10 volts. You're given R, 470 ohms. Your job is to calculate current. So you remember that I is equal to V divided by R. In this case, 10 volts divided by 470 ohms. In decimal form, it calculates to be this long number in decimal. And that's really awkward for us to write down on a piece of paper. We don't have the time, we don't have the space, and if we try to copy this, it's probably prone to error. Now, if you set this to scientific notation is given as one digit one decimal point, and then the rest of the value followed by some power of 10, okay? In this case, works out to be this scientific value, amps. Now, engineering notation works a little more sophisticated in this fashion, that if we have this value here calculated, this works out to be 21, 27, 65, 10 power of negative 3. And I'll show you how to do this on your calculator. This works out to be milliamps. A 10 power negative 3 is milliamps. And how do we get that? I'll show you in the next slide, because very, very important next table for you to learn. And we would write the answer as 21.28 milliamps, properly rounded to 2 digits after the decimal point. How do we get here? Let me show you how. Don't fret. All right. This is something some of you have already become familiar with. We have the Summer Olympics in France coming up in a couple of weeks of 24, and kilo. Kilo is a symbol K. So we have the column of symbols, a column of what we call metric prefixes. Metric prefixes are used in engineering / metric notation. And the prefixes are always expressed with exponents that are multiples of 3. So take a look at kilo. Kilo shows 10 exponent 3, which means 10 times 10 times 10. What is that? That's 1,000. So kilo is significant in the Olympics because we're running kilometers. A 50-yard, not 50-yard, a 10-kilometer run or a 2-kilometer run, something of that sort, measured in kilometers. If we take a look at the graphic that's shown here, this may help distinguish some terms that are commonly mixed. You have something known as a power. A power is a combination of some base that is raised to some exponent. The exponent is a superscript value written in an upper right-hand corner of the base. And the combination of these two in this particular case is called a power. The base is what is going to be multiplied by itself this number of times by the exponent. So if you see right here a power that is a base of 10, the exponent of 3, what this means is 10 multiplied by itself 3 times. 10 times 10 times 10 gives you 1,000. That is a combination of a base and an exponent giving us a power. Take a look at the next one, mega. You've seen mega used in a number of applications. Mega is 10 to the exponent of 6. So this power means 10 as the base, there's the base, multiplied by itself how many times? 6 times. So that's 10 times 10 times 10 times 10 times 10. You do that on a calculator, you're going to get 1,000,000. All right. So what you'll notice is each one of these separate prefixes is separated by exponents that are multiples of 3. So 3, 6, 9, 12, 15, 18, going in big numbers. And then in the other direction, -3, -6, -9, -12, 15, 18. These are really, really small numbers, okay? You've heard these terms, gigawatts, or gigabytes. In fact, in your cell phones, you're very concerned when you upgrade a cell phone, how many gigabytes of memory does it have? Well, we're measuring giga with a capital G, okay? And what does giga stand for? 10 exponent 9, a billion. And some of the hard drives that you have on desktop computers and some laptops are now in the terabyte range for size of their hard drives. And tera is the metric prefix given by symbol T. So I want to go through the whole thing with you, but it behooves you to transfer this into your journal, specifically the way that this is laid out. Now, going in the small direction, 10 -3 is thousandth. So there's an association here. 10 +3 is thousand. 10 -3 is thousandth with a TH. 10 +6 is million. 10 -6 is millionth with a TH. So everything with a TH means we're going in a smaller direction. Everything with a negative exponent means we're going in a smaller direction. And you may have heard of nanobots, okay? Some really, really small robots. So a milli is a thousandth, a micro is a millionth, nano is a billionth. And they all have very specific symbols. Now, these symbols are going to be very important to you on the recommended calculator. And we'll talk about that in just a moment. But on the recommended calculator, you need to be able to distinguish a capital T, capital G, capital M, lowercase k, lowercase m, this thing that looks like the letter U, a lowercase n, p. All of these happen to be on a very special model of calculator. I guarantee you will make your calculation life so much easier if you use the recommended calculator. All right, let's go on to the next one. Here we go. Okay. You do not need this mega $100 TI Inspire CX color graphic calculator. Not necessary if you have the funds and you need to stroke your ego. Put your money somewhere else. You really don't need this unless you are planning to be a math major and go on into physics because it is a nice calculator. I happen to own several different of this series. The most common calculator that many of you will have is something that looks like this Casio 115 ES, and there happens to be what we call essential buttons. What are essential buttons? If you do not use the recommended calculator, and you'll see the recommended calculator in a moment. If you don't use our recommended calculator, then these buttons that I'm describing here are absolutely essential. They're critical in order to make your life easier in calculations, because I highly recommend you work smarter, not harder. What are those buttons? You better see ENG, a whole button all by itself, ENG. Right over here, you see ENG. Now, sometimes ENG is written above the button, which means you have to hit a shift before you hit the ENG function, which is above a physical button. But ideally, ENG is its own separate button, as shown in both of these calculators here. The other button that is critical for your success is the 10 power of X. The 10 power of X is how we key in our engineering exponents. And so 10 power of X is shown here, and on this calculator it's shown as EXP. EXP in this case as a separate button and 10 power X as a separate button, they are the same. They serve the same function. They allow you to enter powers of 10. Now that's if you don't use the recommended calculator, you have to have these. This is absolutely essential. Now, what this means is you'll have a few more button presses in order to get the same result. So the recommended calculator is, I found this one here, the CTI free, it's made by Casio, and it's a CTI free FX991MS. It is the updated version of the calculator I have on the left. I've used the one on the left for many years. It's FX115MS. And a number of the videos that, slides in the videos that I'll be showing you may show you some screenshots of my calculator, but most important thing is they work the same, okay? And I have an affiliate link here. They'll take you directly to Amazon where you can order the recommended calculator, this one, that's great. And it's like less than 13 bucks. So it's really, really worth your while to convert if you already have a scientific one and you don't have the essential buttons, which is engineering EXP. And the reason why these are recommended is, check this out. There's an M for mega, G for giga, T for tera, this U for micro, milli, kilo. These most commonly used engineering prefixes happen to be on the face of these calculator buttons. And so entering a kilo value with these calculators that happen to have the engineering metric prefixes printed right on the calculator is a godsend. If I go back just a moment to the previous one, it does not exist on this calculator in the middle. you have to go through a few more steps in order to enter a value known as kilo or milli or micro. Whereas on the recommended calculators, the buttons are already designated as the second function. So in order to enter kilo, if you wanted to enter 5 kilo, you do Shift K. Okay, so you key in 5 as the numeral, and then you do a Shift K, and that will give you 5 kilo. And it's much faster than the alternative with the standard calculator. Also notice the display. The display will show you the engineering prefix automatically. You don't see a power of 10, which you have to mentally convert to some engineering prefix. The prefix comes up here. As long as you've entered these values correctly, boom, it comes up beautifully. So here, why do we recommend this calculator? Well, it allows the most direct entry of engineering values and the most immediate reading of the results in the correct engineering prefix. It eliminates mental juggling of which engineering prefix is associated with which power of 10. And so in this particular case, if I'm looking to key in 10, divide by 470,000, yeah, I could key this in as 470, followed by 3 more zeros for 470,000. Or I could do this more elegantly, 10 divided by 470. And if I want to hit that K, I do a Shift, tap this number 6 button, which will be the K button. So number 1, hit Shift. Number 2, hit this K function. Number 3, hit equals. And lo and behold, you will see the micro symbol come up. And this tells you that if this were 10 volts, 470 kilo ohms of resistance, this will calculate to 21.276596 microamps. Micro. And that's what it is we have here. Keystrokes are 10 divided by 470, Shift K. Answer is displayed with the correct engineering prefix, this letter U for micro. Very, very nice. Okay, next, we'll take a look at this. Boom. Just to revisit, engineering notation is the same as metric notation. They are not the same as scientific notation. They are not your normal decimal mode. So in the previous slide, 12, I had 10 volts and 470 ohms. If we're looking for current, remember, I is equal to V divided by R. So in this case, it would be 10 divided by 470. And we give us this number in the yellow highlight in decimal mode. And I said in decimal mode, we don't want our calculators displaying in decimal mode because it's too tedious and time consuming and error prone to copy that onto any answer sheet. So back in middle school, you learned about scientific notation, which is given as 1 digit followed by a decimal point, followed by the rest of the digits, followed by 10 power of something. And so 10 volts divided by 470 ohms is given as 2.1276595 times 10 to the negative 2 amps, which is shown here on the display. So I've got decimal calculated. I've got this display shown in scientific notation. Both of these are useless to us. Now, once you calculate either one of these methods, depending upon how your calculator is set up initially, all you have to do is hit that magic ENG button, just touch it once, and the value, either decimal or scientific, will automatically convert to engineering, the appropriate engineering power. And shows 10 power negative 3. This works out to be 21.28 milliamps after we properly round this to 2 digits after the decimal point. You don't need to write down all the rest of these digits. You only want 2 digits after the decimal point. And there's a discussion on how to round in the next slide. Right here. Doop. All right. There's rounding off rules and proper engineering rules. I'm not going to read this to you. You'll just look at this in your own time, but there happens to be some handy videos that do show you how to round any of your decimals to the nearest hundredth. So this is one video, this is a separate video. And so if your calculator example shows 34 point and a bunch of digits, your rounded answer would be 34.36 because we're rounding to the hundredth. Why? Look at these two videos. Proper engineering notation will never be, very seldom, I put down never, but actually very seldom shown as a decimal engineering prefix number of volts, amps, or ohms. Very seldom is that value expressed as a decimal. Very seldom engineering notation is expressed with anything more than, more than 4 digits. Come back here. More than 4 digits in front of the decimal point. So proper engineering notation, if we go to do these calculations that's shown on the next to the last bullet point, in scientific form, this answer shows here, but after pressing the ENG key, you will have the appropriate engineering power, 10 negative 6, and 10 negative 6 works out to be micro, and current calculates to be microamps, and properly rounded, this 340.4255 works out to be 340.43. Why do we need to do rounding and follow these rules? It allows our answers to be more consistent with each other, okay? So some of you are not writing a bunch of decimals or writing too many digits or too many digits after the decimal point. We're all consistently using the correct metric prefix and using the correct rounding to 2 digits after the decimal point. It's for consistency. All right. Your calculator. Now, this may not be your calculator, but this is the recommended calculator. And but you could do this with even a kitchen calculator. This is a pretty easy circuit here. So for this series circuit, I've got a schematic. It shows 5 volts, 100 ohms. So the voltage is 5 volts. The resistance is 100 ohms. What's left? I have the V, I have the R. What's left is I. So what do? Again, take your thumb. Put your thumb over the letter I. What do you see left over? You see a V over an R. Guess what? The formula is I for current is equal to voltage over resistance. So if you look at my notation here, V is equal to 5 volts, which is voltage from the DC power supply. R for resistance is equal to 100 ohms. That's the resistor from your resistor packs, because you're going to pull one out shortly. I is the symbol for current, which calculates as V divided by R, which is 5 volts divided by 100 ohms. And the calculator keystrokes works out to be 5 divided by 100, and this is equal to 50 milliamps. If you use the designated calculator, the very first button you press is 5. The second button you press is divide. The third button you press is the 1. The fourth and fifth button, because there's 2 zeros for 100, you press this 0, 0. And then step number 6, you press the equal key. And lo and behold, the calculator will show you on the recommended calculator 50 with milli shown in the as a subscript telling you that this is in milliamps, and that's milliamps. Now, we're going to verify this with our measurements in just a moment. But let me pause this for just a moment and show you what happens when we use a different calculator that you might have if you don't have the recommended one. So this is 5 divided by 100 is our calculation. Okay, I've switched off the share screen and gone to my camera, and using a more standard scientific calculator without the fancy prefixes built onto the screen, such as what this one has. This one has the kilo, the milli, the micro, the mega, the giga, and the tera. That's already built into this calculator. But if you don't have this or variation of this, you have a more standard scientific calculator. I said that the essential buttons, absolutely essential buttons you got to have is something that says 10 power X. And if it doesn't have 10 power X, it better have the EXP button right here, okay, because they both serve the same function. And then in addition to that, you've got, I highly recommend a separate ENG, engineering button. All right, so let's go ahead and turn this puppy on and do the same calculation. Turn this guy on, and we're going to do 5, and we're going to divide, so hit the divide key, and 100, so 100, so we've done that. And then we're going to hit equals. And when we hit equals, guess what? This comes up in scientific notation. This is not an exponent that is some multiple of 3. It's useless to us. So don't even bother with scientific notation. If you see a power here that's something other than 3, 6, 9, 12, or -3, -6, -9, -12, if you see something other than some multiple of 3, then what are you going to do? Hit the ENG key, because once I touch the ENG key, bam, it automatically goes to show you 50, 10 power -3, which is really nice. But this behooves you to do one more thing. If you don't remember right away what 10 power -3 is 10 power -3 a nano? Is it a micro? Is it a kilo? What is 10 power 3? Well, hallelujah. Thank goodness you followed my advice success tip and you transcribed that engineering prefix table into your journal. So as it is on your journal on the side, you see that 10 power -3 is in fact milli. Isn't that nice? So the not having the recommended calculator means you're just going to be pressing a few more buttons than our recommended calculator, and it's not a big deal. You'll get used to it, and I just like to promote that my students work smarter and not harder. And with anything other than the recommended calculator, you are definitely working a little harder, not much harder, but a little harder. All right, let's go ahead and do this. Okay, so we go back to our slide set, and lo and behold, isn't it nice that your recommended calculator doesn't even give you some power of 10? It gives you the actual engineering prefix, which you will write down as lowercase m, capital A for 50 milliamps. Sweet. Now, we're going to verify what all of what's going on here, and that is we'll build the circuit, a 5-volt source, which you have on your DC power supply, 100-ohm resistor, which you have many in your kit. We've used this in the previous training videos, and you're going to build the circuit that we've done before. Now, I'm doing this on a half-size board just to make things a little more concise in the view screen, but as you can see, my jumper is set to positive 5 volts at the top. My jumper is set to the off position with the middle 2 pins at the bottom. The power supply is lit because I've pressed the button and connected the USB cable. I have a red jumper wire from the red rail coming down to row 10. And on row 10, I've got the long lead of the LED here, short lead of the LED on row 12. Connected to row 12 is one lead of my resistor. My resistor jumps all the way over here to row 20. And row 20, I have a connection with the black wire, which takes me all the way back to the blue rail. So the electrons leave the blue rail, the negative side of the power source. The electrons flow through the black wire, underneath the board, through this resistor, then underneath the board again to this lead of the LED, through the LED to light it up, then underneath the board again to this jumper wire, which takes us to a return path to the red power rail. So first thing you want to do is confirm you've got a good circuit built with the appropriate ohms that you've pulled out of your kit, and you want to make sure that the on LED shows you the current is working. Now, when we go to do our measurements, we will yank the LED out because the LED is only to show you that things are working. Now, what we're going to do, we have to confirm the resistor value. Just because you yanked it out of the bag doesn't mean you yanked the correct one out of the bag. So we have to confirm that the resistor that's on the board is in fact the 100-ohm resistor, because the schematic specifies it as 100 ohms. This better be the 100-ohm resistor. So how do we do that? You confirm the resistor value by first what? Removing the test LED. You can see the LED is gone between row 10 and 12. It physically removed it. If you don't recall that LED being there, boom, there's the LED between 10 and 12. So I'm going to yank this guy out, and by yanking this guy out, and then now hooking up my ohmmeter leads, and you can see the multimeter is set to the ohm position, the omega, and the display is in units of ohms. There's a little omega symbol here. And by touching one probe to one end of the resistor, one probe to the other end, I can measure resistance. Essentially, what is critical is that the power supply is off. It is. And, and you have to confirm that the power is disconnected, meaning this red jumper wire cannot be anywhere near touching the same row as to this end of the resistor. There's a break between this resistor and this jumper wire where the LED used to be. Okay, so there is clearly a disconnection of power. So only when the power supply is off and you have a disconnection of power can you measure the resistance of a resistor on the board. And it says here the black and red probes can go on either side of the resistor and you take your measurement. There's no need to have red or black on any particular side because the resistor is not polarized, okay? And you can try this. You can put red on this side, black on this side. You'll get the same value. So it's supposed to be 100 ohms. Does it measure 100 ohms? It measures 101.1. That's pretty close to the tolerance value of these resistors. They're never going to be exact. I guarantee you they're never going to be, well, very seldom are they going to be exact. As long as we're close, we're happy campers. Okay, so you first thing to do, confirm resistor value. Then after you've confirmed the resistor value following these steps, then what you're going to do is confirm the voltage. How do you confirm the voltage? You turn the power supply on. And again, there's a break in the circuit. There is no connection between this jumper wire and this resistor, purposefully left broken. But the way we confirm the power is we can take our red probe and go directly to the metal pin of the jumper wire that's connected to the red rail. So it says red probe to the plus power rail pin, which is right there. And then it says the black probe touches the metal of the jumper wire that's connected to the blue rail. And in doing so, if these are properly connected, and your multimeter is now, see, we'll look at the dial, is set to the V position and is set for DC. It's showing voltage, and we want something close to 5 volts. Well, guess what? Your power supply gives you just a tiny bit more than 5 volts. It's okay. It's 5.12 volts for this particular power supply. Some of yours might measure 4.9, some might be 4.08. As long as it's something close to 5, you're a happy camper. It may or may not be exactly 5. Don't fret if you don't see 5.00. Electronics is in this particular case in labs, because there is a variation of tolerance, error, margin of error in the resistors, and there's also some margin of error in the power supplies. So clearly not 5.00. That's okay. We're close. All right, now let's go ahead. What's the next thing we're going to confirm? We're going to confirm current. Now, we did this before, so please follow the video carefully. In the previous video, I blew out a fuse accidentally because I was using the probe, the red probe, as a pointer, and I'm pointing where to touch, where not to touch, and lo and behold, as I was pointing, I accidentally touched the red wire and shorted out the fuse. Anyway, so the previous video shows how to take your digital multimeter apart and replace the fuse. All right, so how to confirm current? You have to connect these probes to the open. Remember, this circuit was split open when we pulled out the LED. There is no physical connection between the red jumper wire on row 10 and the resistor on row 12. There's a gap of 2 rows. So that gap is what we call an open. And it's critical for you to connect the red probe to the plus side of the open, which means it is on the board side of the red wire right here. Do not connect, do not connect both of these probes to the blue-red rails. You'll blow the fuse out really quick. The only place for these probes, red probe goes here, and the black probe has to go on the end of the wire resistor, only on this end of the wire of the resistor, where the open is. If you put this black probe over here to the wrong end of the resistor, you'll blow the fuse for sure. Okay, so I'm describing that. I'm not using the probe tip as a pointer where not to connect. I'm just telling you now, this probe tip has to be on this side. This is where the open is. If you put the black probe over here, there's a direct path for electricity to flow from the blue rail through the black jumper wire into the black probe, through your meter, blowing up the fuse, coming out this side, going directly back to the red rail. It's like shorting the battery terminals of your car. Big sparks, not good. So follow this and you'll be able to get a reading. And if you do so, look at this. It does, when you have your multimeter set to read current in milliamps, so it's set here, and it does show you on the display MA for milliamps. Do we have something close to our calculated 50 milliamps? Here's your calculator display, 5 divided by 100, 50 milli. That's pretty darn close. Why is it not exact 50? You're not going to get exact because the power supply is not exactly 5 volts and the resistance is not exactly 100 ohms. So as long as you have something that's close, and 49.2 is pretty close to 50, we're within the realm of acceptability. Okay, be happy. All right. Now, the next one takes us to a different circuit. This will be our second series circuit. Now, what's different about this? Well, we're using the same 5-volt source. I've changed the resistor to 330 ohms. You're going to do that in a moment as well. But let's go through the slide first before we play with your breadboard. So the formula is the same. You're going to calculate for current. You put your thumb over the letter I. What's left? V over R. So I is equal to V over R. V is 5 volts from your DC power supply. R is a new value. It's not 100 anymore. It's 330 ohms. It's a larger amount of resistance. And this comes from your resistor packs. Your job is to calculate I, and current calculates as V divided by R, which is 5 volts divided by 330 ohms. Oops, come back here. Go. Here, okay. Calculates the 5 divided by 330, works out to be 15.15 milliamps. So on any calculator, step number 1, you take your 5 volts and then you divide. Step number 2 is divide. What are you dividing by? 330. So you hit 3 one time, you hit 3 again, and then you hit the 0, and you get the 330 that's on the display. So 5 divided by 330. Then step number 6, you hit the equal key, and lo and behold, step number 7, ta-da! You've got this showing 15.151515 milliwatt. Well, hopefully, if you've transcribed the information into your journal and you look up current is in units of amperes. What's the symbol for amperes? Capital A. So you would write this as 15.15 milli, capital A. And notice that I've got this rounded to 2 digits after the decimal point. I'm not writing out all of these digits because it's just not space or time efficient. So the rounding and using the correct engineering prefix was discussed earlier. All right, now, nextly, you're going to confirm this circuit build. So with the 330 ohm resistor now in here, reinsert the LED, and as long as the LED is reinserted, this power supply is on, LED is lit. All right, you're a happy camper. You've got current flowing through the circuit, and now we're ready for the next step. Next step is confirm the resistor value. How do we do that? First of all, remove the test LED. Is my LED off the board? Yes. Turn the power supply off. Is it off? Yes. Next, confirm the power is disconnected. Is the power disconnected? Well, look, my red jumper is on the red rail, but where's the other side of the red jumper? Row 10. Where is the resistor? The resistor's on row 12. They are separated by 2 rows. So there is no power connected to the resistor. You can't have electricity flowing through the resistor to try to measure ohms. So then you take your red, black probes, put one on either side of the resistor, okay, because the resistor is not polarized. You put red here, black here, or put red here, put black here, it doesn't matter for a resistor. And you set your multimeter for omega, and it better show omega on the display. And hopefully you have something close to 330 ohms, and this shows 335.9. We're close. Okay, it's not going to be 330 exactly. I explained earlier, just as long as you have something that's reasonably close. And you record that value down. And notice that the plastic bag here shows I've yanked this resistor out of the 330 ohm bag. All right. Now, next, we're going to confirm the voltage. And by confirming the voltage, we're going to turn the thing on. So let me do this. Okay, so we're going to confirm the voltage. Voltage in the schematic specified as 5 volts. We will connect red probe to the jumper wire connected to the red rail, right to the metal pin. So pull this up so a little piece of the metal is exposed enough for the probe to touch it. And the black probe goes here. And these connections are only when you're confirming voltage. So you make the connection, you turn the power supply on, red probe to the red power rail pin, black probe to the negative power rail pin. Your digital multimeter is in the V mode, voltage mode, and your display shows you volts. Only when it's all set up this way do you make the connections this way. And something close to 5, in this particular case, your power supply, this power supply gives me just a scoosh more than 5. Next. Did I actually skip one? So we have this. We did the ohms. Okay, yes. Now we do the voltage. Now current. Cool. All right. So what did we calculate previously? 5 divided by 330 ohms works out to be 15 milliamps. Okay. So in this particular case, we want to set our multimeter to the milliamp position. We want to show that the display actually shows milliamps. And again, the only place to put our probes for measuring current is at the open, never ever where we had hooked up the probes for voltage. Only here. Never put this black probe on this side of the resistor while the red probe is here. That'll blow out your fuse really, really quick. So the open is created between this red jumper wire on row 10 and the resistor on row 12. And by hooking your probes up this way, the electricity flows through the resistor up this probe into your meter, giving you the reading out of the meter, down through this probe, and following the red wire back to the red rail. That's how your continuity is maintained. Your meter becomes part of the circuit. And so does this confirm, does the measured value confirm something pretty darn close to the calculated value? Yeah, and I said they're not going to be exact, but are they going to be close? Looks pretty close. Next. All right, here's where things start to get fun. And that is, more often than not, you're not going to be playing with resistors that are in the hundreds of ohms range. Very often, you're going to be playing with multiple resistors that are certainly into the thousands, into the kilo range. So this example shows same 5-volt source in the schematic. The resistor is now a 5.1 kilo ohm resistor. You do have this in your pack of resistors. And so if we're looking for current, and again, we refer to the triangle, cover the I, that's what we're looking for. We're looking for current, which is shown by the letter I. Cover that with your thumb. What do you see left over? V over R. So I is equal to V over R. V is 5 volts from your power supply. R resistance is equal to 5.1 kilo. It means this is 5.1 thousand or 5,100 ohms. That's a lot of ohms. And so this comes from your resistor packs. So current is calculated as V divided by R, or in this case, 5 volts divided by 5.1 kilo ohms. Your calculator keystrokes are so easy on this calculator, the recommended calculator, because I'll show you what you need to do. It's 5 divided by 5.1, shift K equals. That's it. So step number 1, 5. Touch that button once. And what we're going to do, step number 2, divide. So there's your 5, divide by. What are we dividing by? 5.1 kilo. So the third button pushes, you can push this 5 again. Then number 4, you're going to hit the decimal point. And then number 5, you're going to hit the number 1. So there's your 5.1. Then how do you bring in the symbol kilo? On this calculator, it's so easy. You just have to go to step number 6, touch the shift button, And the shift button brings in all of these second functions above the keys. And in this case, a shift button will bring us, by hitting the 6 button, this will give us the kilo function. And when you go to do this in step number 7, by hitting shift and then touching that 6, you will see kilo come up in your display. Pretty sweet. Then step number 8, hit the equal sign, and step number 9, confirm your calculator display, 980.39 micro. And what did we calculate? We calculated 980.39 microamps. So our calculation so far is jiving with my notes, and hopefully you've done these button presses. Now let me show you for a moment how we do this on the other calculator that does not have the engineering prefixes. Same calculation. You should write this down in your journal. 5 volts divided by 5.1 kilo ohms gives us these 980.39 microamps. Okay, so on a more standard scientific calculator, you turn the puppy on. And it was 5 volts divided by 5.1 kilo. So here's the 5. Let me not do this with my finger. Here's the 5. Boom. It appears. You hit divide. So we hit divide. Divide shows, and we want 5.1. So it's 5.1, 5.1. 1 didn't appear. There's the 1. So 5.1. And there is no kilo button here. How do I bring in kilo? Well, you have to go to your metric units chart that I showed you earlier. Hopefully you've transcribed that into your journal. And you know that kilo, by looking at that up, is 10 power of 3. So luckily we have a 10 power button right here. So all you have to do is touch the 10 power key once, and it shows you times 10. And then kilo has an exponent of 3. So you touch the 3 and you can see times 10 power of 3. That's how you enter kilo on this calculator. Then you hit equals. And when you hit equals, the calculator ends up in either decimals or scientific notation. And as I said, we know this is scientific notation because this exponent is something other than some multiple of 3. So this is useless to us until we hit the engineering key. So once I touch the engineering key, voila, look at that. 980.39, 2157. That looks very, very similar to our calculator display a moment ago, except instead of the little letter U, the micro symbol in the upper corner, the regular scientific calculators show you the 10 power, whatever exponent's appropriate. So in this case, it's 10 exponent -6. Well, if you haven't learned it by now, again, you go back to your journal, go back to your chart, and look at 10 power -6. And 10 power -6 is, in fact, micro. So then you write down 980.39 microamps. 980.39 microamps. So it's just a few more steps with something other than the recommended calculator, but you'll get there. Okay, so back to our slides, you can see on the lower right-hand corner of your screen, 980.39 microamps. And as I've said, the recommended calculator does show this in the proper engineering prefix. So let's go ahead and continue we're almost done, but to the next one. Here we go. We're going to verify Ohm's law with current. And how we've done this before, we stuck the LED in, and we have a 5.1 kilo ohm resistor as designated by our little plastic packet with the label 5.1 kilo ohms. That's here, and we stick the LED in, power supply's on, the thing doesn't light up. Uh-oh, did we build this wrong? Double check. Red jumper wire is where it's supposed to be on the red rail. It comes down the row 10. Long lead of the LED is connected to row 10. Short lead is row 12, connected to the resistor on row 12. This comes over to row 20. Jumper wire for the black jumper wire taking us to the blue rail is here. You want to make sure if things don't light up, just pull each of these up and down just a little bit, just in case there's some contaminant inside the little hole. It is not in this case. There's a reason why the LED won't go on. But if something were to happen, most of you would very quickly take this LED and flip it around because maybe you got the long lead and the short lead reversed. That's typically what happens when an LED does not light up, okay? But no, it turns out in this case, the long lead is where it's supposed to be in row 10. Short lead is where it's supposed to be in row 12. This puppy don't light up. Why? Here we go. You cannot yet confirm good circuit build with the 5.1 kilo. Yet. You can't yet. Doesn't mean you can't, but you just can't yet. And the reason why the LED doesn't light up, your test LED cannot light up. Why? Because the resistance, the R value in this case, is too high. It's 5,100 ohms. When you think about the first two circuits, the first circuit was 100 ohms. The second circuit was 300 ohms. So the LED was a little dimmer. But this is 5,100 ohms. That's a lot of resistance. That's a lot of constricting of the water pipe. There ain't much current going through. And if the current is not high enough to trigger that LED on, it's going to be off. So the current being too low means this LED is just not going to light up. So don't fret. First thing you do is, do all the little circuit pull ups and pull downs and make sure you've got good connections. Make sure everything's on the proper row. You've done all that. It's just not going to fix this particular LED from lighting up. So what do? Don't yell and scream. Simple. Watch this. Okay. How did we confirm the resistor value before? All right. You want to confirm the resistor value by removing the LED, which you've done. Turn the power supply off, which you can see we've done. Confirm the power is disconnected, which we've done, but I want to review that with you. Red jumper wire, red rail, red jumper wire in row 10, resistors on row 12. There is no connection between 10 and 12 where the LED used to be. So the power is in fact not only off, but disconnected. Then red and black probes can go on either side of the resistor. Your multimeter dial is set to omega for reading ohms. Your display is showing you units of kilo ohms. And is the display showing you something close to 5.1 kilo? Well, 5.08 is pretty close to 1. It's within 20 ohms of being 5.1 kilo. Okay, so what we got going on here is we're happy with the resistor value. Then what you're going to do next is this. Boom. Confirm the voltage. We've done this many times before, and that is you confirm the voltage by turning on the power supply. It's on, the LED is lit, and you take the red probe to the red power rail, you take the black probe to the blue power rail, and you read the value. Your multimeter is set to read voltage. The display shows you V, that's going to show you voltage. Is this something close to 5? Well, lo and behold, it's 5.12, which is great. Not going to be exactly 5. And as I've said, don't fret if your value works out to be 4.9, 4.98, 4.9, something less than 5. As long as it's close to 5, we're happy. All right, so you confirm the voltage. Then what are you going to do? Then you go to confirm the current. And this is the same as what we've done before. The only place where you can connect these probes is where the open was created, where the LED was. The red probe goes to the board side of the jumper wire. There's the board side of the red jumper wire. The black has to go on this end of the resistor, not the other end. You hook up the black probe on this end, what's going to happen? Sadness. Your fuse is going to blow and you're going to have to acquire a fuse and change it out like I showed you in a previous video. So black probe goes here because this is where the open is. And if you've got everything built properly, the rest of the circuit is built properly, power supply is on, and these are hooked up properly, then your multimeter, you want to set the dial to read current, so milliamps. You want to make sure it's in the DC mode, and the display shows you milliamps. Wow, check this out, 0.99 milliamps. Well, how come it doesn't say micro? Well, your display doesn't have a micro, but it's showing you something that's less than 1 milliamp. Less than 1. So what's less than 1? That's looks like it's reading 990 microamps. And the conversion between this and this 980.39 microamps is what we calculated. They are essentially the same. Okay, you look at this and say, nah, it looks a little disconnected here. I can't quite make it out. What is 0.99 milli? Is 0.99 milli actually something close to 980 micro? Well, what's shown in the calculator on the right-hand side is in fact proper engineering notation. The decimal point preceded by no more than 3 digits, and the appropriate engineering prefix shown right there. That's proper engineering notation. Your calculator shows you this with the metric prefix 0.99 milli. I'm going to show you in just a moment 0.99 milli is in fact something very close to 990 micro. So we're going to do this. Pause here and switch to camera. All right, so we're going to review the math. The calculator is on. We're going to take the 5. We're going to divide by 5.1. Okay, and here I can't hit the kilo, so I have to use my 10 power key. So I'm going to do 10 power. And kilo is what power of 10? It's the 10 power 3. So after hitting the 10 power key, I key in 3. So there's my 5 divided by 5. Sorry. 5 divided by 5.110 exponent 3. So that's my 5.1 kilo. Now I'm going to hit equals. And in equals, what we've done before is to show you something. Oh, well, it's in scientific notation that's useless to us. We remember to hit the ENG key, touch this one time, and it brings us over into proper engineering notation, meaning decimal point preceded by no more than 3 digits. And how are we going to round this off? 980.39 microamps. But you say, okay, we've done this before. I'm happy with how to do this in a regular scientific calculator. How does this jive with the 0.99 milli? Well, check this out. I'm going to clear this out. And I'm going to key in 0.99 milli. So 0.99, so there's the 0.99. Milli, if you recall from looking at the engineering prefix table, which you've transcribed into your journal, is 10 power negative 3. So here's my 10 power key. And then I have to hit the negative, and the negative is not minus. It's this button here that's shown in parentheses, the negative symbol in parentheses. So I have to hit this guy first. So I have 10 power negative, and milli is 10 power negative 3. So now I hit the 3. So let me confirm what I've got in here. 0.99 10 power negative, oops, sorry. 0.99 10 power negative 3. Is that what our multimeter showed us? 0.99 milli. Yes, it did. Watch what happens when I hit the equal key. I'm purposely keying in something that our multimeter showed us. It didn't show us microamps as we hoped. It showed us 0.99 milli, and milli is 10 negative 3. If I hit the equal key now, it translates that into scientific notation. And then if I do this, touch this once, there's my engineering notation. And guess what? It is 990, 10 power negative 6. And 10 power negative 6 is what engineering prefix? It's micro. So yes, this 0.993 milli is in fact 990 micro, which is pretty close to what we had calculated. All right. So don't be afraid to see values on the display of your multimeter that are something other than what your calculator coughs up. And in fact, I do this with a variation on your recommended calculator. Let me just go ahead and do this one. This is a previous version of your recommended calculator. So it's on. And so I'm going to do 5. Oh, no, actually clear. I'm going to do 0.99. And how do I key in milli? So milli in this particular case is represented as a second function, this m right here. So how do I hit the second function? I hit the shift key. So I did shift, boom, and hit the milli key, boom. Look at that, 0.99 milli. On this other calculator, we had to key it in as 10 power negative 3. On this calculator, we can go right to the engineering prefix milli, and then if I hit equals, bam, this automatically skips the scientific notation and jumps directly to engineering notation, 990 micro. So you've saved yourself quite a few steps in your work by using the recommended calculator. And yes, this is different appearing than the one I have in the slides, because like I say, this is an older model that I've used for many years, but functionally it's the same as the updated model that I'm recommending in our videos. So with that being said, let me go and so just go ahead and look at our last slide. And our last slide again shows us 0.99 milli, and 0.99 milli is 990 micro. And again, it's not exact to the 980 micro, but pretty close in the world of tolerances. Keep in mind, we didn't start off with an exact 5. We didn't start off with an exact 5.1 kilo ohms. So given some variations there, the current's going to vary a little. Now, when you go to do this, you might not even see 0.99 milli. You might see 1.0 milli. 1.0 milli is 1,000 microamps. Okay, just because that's what the calculator internally calculates. It might, for whatever reason, show this as 1.00 milli, a whole milliamp. And a whole milliamp is 1,000 microamps. And again, given the tolerances or margin of error, it's not a whole lot far away from 980 micro. Okay, so don't fret if your digital multimeter shows you 1.0 milliamps, but hopefully it shows you something that is a decimal 0.99 or 0.998 milliamps, and the decimal milliamps does work out to be microamps in the conversion process that I showed you. Okay, we're done with this. We will have many more fun things to do with voltage and resistance in the upcoming videos. So thank you so much for your attention. If this was useful to you, hit the like button. If you like this series, hit the subscribe button. And when you hit the subscribe button, then the videos as they're created will be announced to you via ping to your cell phone. You say, oh, Code's got a new one. And that brings you to be able to see what the latest and greatest video is. And the affiliate links are available in the narration portion of the YouTube. So they will show links directly to Amazon of where you can acquire the recommended devices. And if you want to support the channel by being a Patreon, then please do. And that will help allow funding to happen minimally to whatever your heart desires. That will allow me to continue making these videos. And again, hopefully they're helpful to you. So with that being said, cheers. The KOGUY is signing out. Thank you so much. Adios.